Welcome to Math 30-2, where we have been studying logarithmic functions in Chapter 7, and we are in 7.5 today, the last lesson of the chapter. And in this lesson, we're going to get into using logarithmic regressions. Now, we've already done linear regressions, quadratic regressions, cubic regressions, sinusoidal regressions, exponential regressions. So the steps that we're going to go through will be very familiar. It's just now we're doing it with a logarithmic function instead of with one of those other functions we previously looked at. Now this lesson begins with a number of review or warm-up questions, like 2 pages worth in our notes. So if you've already done this in person, feel free to skip ahead to the example where we will actually be doing logarithmic regression. But to begin with, let's look at some equations here, and we want to know if these equations are true or false. So if you haven't already done these and reviewed them in class, then pause the video at this point and work through the 6 questions on this page and state whether these equations are true or whether they're false. Then restart the video and I'll go over the answers with explanations. Well, for question number 1, hopefully you said, this is a true statement. And it's a true statement because if I look at the right-hand side, here I'm dividing powers base 5. So just a reminder, if I had something like 5 cubed divided by 5 to the exponent 1, we would say, well, if I was to evaluate this, this would be 125 divided by 5, which is 25 or 5 squared. And I expect that you remembered the rule that said when we're dividing powers with the same base, we can subtract these exponents. So this is the same as 5 to the exponent 3 minus 1, as if we'd subtracted those exponents to get to this point of the 5 squared. Here, this is a similar idea. Since I'm dividing powers with the same base, I can subtract the exponents. So the base stays the same, but the exponent of my numerator goes first, and then I subtract the exponent of my denominator, which was a 1, and that's equivalent to the left-hand side. So, true statement. Question number 2. Well, once we have question number 1, hopefully you fairly quickly recognize that question number 2 will also be a true statement. And here, to begin with, as we look at what we have in the numerator here, when I'm multiplying 2 powers, then that means that in order to evaluate, I can add the exponents. So that's the same as 5 to the exponent x plus x, which is 5 to the 2x. And again, if I looked at an example where I had 5 cubed times 5, that would have an exponent of 1. Well, this is telling me here that I have 3 5s being multiplied together. And then here I have 1 more 5. So in total, I have 5 as a factor repeated 4 times, which is the same as 5 to the exponent 3 plus 1, adding these 2 exponents together. So since we have a 5 to the 2x in the numerator, a 5 in the denominator, it's actually equivalent to what we had in question number 1. Let's look down to question number 3. Well, question number 3 ties back to the other 2 as well, because even though I have a 25 in the numerator here, I could say that 25 is equal to a 5 squared. So if I have a 25 to the exponent x, then that means I have 5 squared to the exponent x. And when I have a power raised to an exponent, I can multiply those exponents, which gives me 5 to the exponent 2x. And again, suppose I had, well, let's not do 2, let's do 5 again. Suppose I had 5 squared to the exponent 3. Well, this exponent of 3 tells me that I have 5 squared repeated as a factor 3 times. And then using that rule that we just talked about, multiplying powers with the same base, we can add the exponents. So that gives me 5 to the exponent 2 plus 2 plus 2, which is 5 to the exponent 6. Same answer as I would get if I was to multiply these two exponents together, 5 to the exponent 2 times 3, which gives me 5 to the 6th. So what we showed up here is that this numerator is the same as 5 to the exponent 2x, which means, again, my right-hand side is equivalent to question number 1, and this is a true statement. Now let's look at these logarithmic equations. For number 4, I hope you said this was a false statement. And it's false because what happened with whoever imagined that this would be true is that they thought of this logarithm as being multiplied to the x. If I had something like 2x over 2y, I can think of this as 2 over 2 times x over y, and this 2 over 2 reduces to 1. So they can cancel out. The reason that happens is because this 2 and this x are being multiplied. But this logarithm and this x, even though they're written beside each other, are not being multiplied. So we can't just cancel out those logarithms. That is illegal math. It's an operation being done here. So this is a false statement because we can't just cancel out those logarithms. We only cancel things out when they are part of a multiplication statement. Here the 2 was multiplied to the x, here the 2 multiplied to the y, so the 2's we could cancel out, common factors. The logarithm isn't a factor because there's no multiplication in that question. So let's look at number 5. On the left, we have the division of logarithms, and on the right, we have the log of subtracting 2 powers. Well, this is close, but not quite the law of logarithms. What the law of logarithms says, when we are subtracting inside the logarithm, remember a logarithm operates on powers. Oh, well here this means I'm subtracting powers. We don't have any rule for subtracting powers. The rule that we do have is that if I had the log of x divided by y, this would equal the log of x minus the log of y. Why is this true? Well, this is true because logarithms operate on powers. Here I have a power divided by a power. A logarithm is an exponent. So here I have, when I'm dividing powers, it is the same as subtracting the exponents as long as the bases are the same. And we can see from these logarithms, they're both base 10 logarithms. And over here, this was also a base 10 logarithm. So we're imagining this x to be a power base 10, and we're imagining this y to be a power base 10. So since we're dividing powers base 10, I can subtract those exponents. This equation up here is a distortion of this idea. This is saying dividing logarithms is the same as subtracting their powers. That is not true. Now, as a bit of a reminder, this left side where we're dividing logarithms, that is the change of base rule. So we could say that that side is equal to the log base y of x. So the left side is equal to this log base y of x. That's the change of base rule. The right side, we don't have any rules that applies to. So false statement. Then as we look at number 6. On the left, we're dividing logarithms. On the right, we're subtracting logarithms. Again, that's a distortion of this law of logarithms. Remember, Subtracting logarithms is not the same as dividing logarithms, so this is a false statement. Subtracting logarithms happens when we were dividing the powers inside the logarithm. So some tricky questions here as we looked at these logarithms, some easy mistakes to make. And since they're easy mistakes to make, I'd encourage you to keep your formula sheet handy to make sure that you use the laws of logarithms correctly. Okay, there's our first set of review questions. Our next set is looking at solving equations, which we learned in our previous lesson. So here we have 3 questions for you to do in review. So at this point, why don't you pause the video, complete these 3 questions, and then restart once you have finished to the end of question number 9. We want to solve exactly using logarithms, so we're going to do this algebraically. Well, the easiest option, I would say, for solving this first equation would be just to rewrite it in logarithmic form. So as I look at this in exponential form, I have a power with a base of 5. So that means I can write this as a logarithm with a base of 5. The logarithm is equal to the exponent, and the exponent is an x. And so my 10 is what the logarithm is operating on. And again, what a logarithm says is, if I was to rewrite this 10 as a power with the base of 5, the exponent would be x. If I was to take this 10 and rewrite it as a power where the base is 5, the logarithm tells me the exponent is x. So there we have an exact value answer. One other way we could have done this question, and we could do it for each of the next couple questions, but I'll only do it for this one, and that would be to take the logarithm of both sides. So I could do the log base 10 of 5 to the x and the log base 10 of 10 on the right-hand side. And then we would use that rule that says a logarithm operates on a power, so this 5 is a power, but it's raised to an exponent, so that exponent I can bring down in front and multiply to this exponent. A logarithm is an exponent. So that would be equivalent to x times log 5. Now the log 10, I could leave it as a log 10, but again, because I'm not given a base in this logarithm, this is a base 10 logarithm, as was this one. So log base 10 of 10 is equal to 1, because again, it says if I rewrite this 10 as a power base 10, what's my exponent? My exponent is a 1. And then we'll solve for the x here by dividing the log 5 to the other side, so we'd get 1 over log 5. So this is also an exact value answer for this question, as is this one that we had on the left side. Well, question number 8 we could do in the same way. We could just rewrite this in logarithmic form. My exponent is the logarithm. The base was a 5, and it's operating on a 9. Now, in the previous question, I showed that we could take the log base 10 of both sides. What I could have done as well would be to take the log base 5 of both sides. So what if I did log base 5 of 5 to the x? If I do log base 5 on the left, then I have to do log base 5 on the right side as well. Then, because I have log base 5 of 5 to an exponent, this is just equal to the exponent of x. So x is equal to log base 5 of 9. So 2 ways of doing this question. And again, we have that third way where we could have taken the log base 10 of both sides. There are actually an infinite number of ways because we could have used any base. It's just in this case, the base 5 is most useful and the base 10 is handy for working with the calculator. Number 9, similar. I'm going to do this that first way where we say my exponent, which is 2x minus 1, is equal to the logarithm. And the logarithm has a base of 5, just like that exponential expression had a base of 5, and it's operating on the 9, which is the power, right? This 9 is equal to this power where the base is 5. Now I just need to solve this equation by doing some rearranging in order to isolate the x. So I'll add 1 on both sides of the equation. And again, as mentioned in the previous lesson, not a bad idea to put in brackets here so we don't get tempted to add the 1 to the 9, because the 9 is being operated on by the logarithm, and that has to happen first before I can add the 1 to it. So at this point, I have 2x is equal to log base 5 of 9 plus 1, and then we can undo this multiplication by dividing both sides by 2. So I could leave my expression as it is, where I have 2 in the denominator of the whole thing, or I could divide each of these two terms by 2. So I could write it as 1/2, that's the same as dividing by 2, times the logarithm base 5 of 9 plus 1/2. So here we have an exact value answer for this question. Well, there are the review questions. Let's get into an example where we are looking at doing a regression. So in this situation, we have some data in table on the right here. We have the age of a tree in years and the height of the tree in feet. So these are some weeping Higgin cherry trees planted in Washington, D.C. I don't know if this is true. I'm guessing so since there's so much detail in this question. At the time of planting, the trees were 1 year old and they were all 6 feet in height. So here we have the average height of the tree is 6 feet when we have the age of 1 year. We are asked to construct a scatter plot on the calculator for this given data. So here, time is passing. And as time passes, we would say that this will be our list 1. These will be our x values. So we'll enter this into list 1. And responding to age is our y values, or our dependent variable, and we can enter that into list 2. So we've done this in the past, so I'm not going to show the process. But at this point, I'd encourage you to pause the video, enter the data from this table, and then construct a scatter plot. Once you have your scatter plot, then restart the video. Well, here's my scatter plot, and I see that as time increases, as we go from left to right, my height is also increasing, but that growth is slowing down. So I get a curve that's going up to the right where it's increasing as you go to the right, but it's slowing down its growth. And hopefully you recognize that this is pretty similar to the shape of a logarithmic curve. So we will do a logarithmic regression to model this data. And I'll pull this out again in a moment, but first let's look at number 11. Determine a logarithmic equation to model the data, rounding the values to the nearest hundredth. Now, when you do a logarithmic regression on your calculator, it will do a log base e, which is a natural logarithm. So you're going to have an ln showing up in your equation. That is a log base e, which we call a natural logarithm. Now, just a quick word of warning when you go to calculate this, doing the regression on a TI 84 Plus, and maybe on an Inspire. It's been a while since I've looked at that, because there are a few regressions that you might get confused with. Your calculator has a lin regression. This is a linear regression. We don't want the linear regression, but it has the L and the N, so kind of at a quick glance, you may make a mistake. The LN is the natural logarithmic regression. That's the one that we want. But there's also one that's a logistic regression, but if you kind of ignore that part, you just see log and you think, oh, this is the one that I want, but it's not the one that you want. So you want to make sure that you're choosing LN regression for the logarithmic regression. So pause the video at this point and complete your regression and then restart the video. Here's my scatter plot, and when I do that linear or logarithmic regression, here's what I'm getting, and I chose to write height as a function of time. If you wrote a y here, that's perfectly fine, and that's what your calculator will have used. And what I'm getting, rounding values to the nearest hundredth, 5.95 plus 6.28 times, so that's what that asterisk means. So that's being multiplied to the natural logarithm of t. Okay, so there's my regression equation. So h is the height of the tree in feet, and t is the age of the tree in years, according to my equation. If you used x and y, it is a good idea for you to explain what does the x represent. That would be the age of the tree, and the y would be the height of the tree in feet. So then we want to describe characteristics of the function. First of all, we're asked to find the intercepts. So here you can see my regression graph together with my scatter plot, and I've calculated the zero of the function, and I'm getting a zero of decimal 38896, and the decimals continue, and that's where y is equal to 0. So that's my x-intercept. Because this is a logarithmic equation, and there's no translation to the left or right, there is no y-intercept. So here we go. We have an x-intercept at about 3.89, rounding to the nearest thousandth, and I have no y-intercept. How did I know where to round? I just guessed. The question didn't tell me, so I just picked a number of decimal places. In part B, which you can't see at the moment on my page, we're asked to find the domain and range. So we want to think about domains for a logarithmic function, but also domains that make sense in the context of this question. So here we would say that, well, having a negative height isn't going to make sense in the context of our tree. So I'm going to say that x is greater than or equal to that 0.389. So I'd say that would be the smallest x value that will make sense in the context of this question, because the negative tree height doesn't make sense. Now, realistically, a logarithmic graph does increase infinitely, but a tree isn't going to grow to an infinite height, but we don't have enough information to know what a maximum would be. I guess that would talk about y values, why the y value is greater than or equal to 0, but I don't have, well, it has to be less than 80,000 feet, which for sure it is, but we don't have enough information to know what the maximum value would be for the range. And similarly for my domain, I don't know what the maximum age will be for the tree, and so I didn't do a maximum, I just did minimum values for both of these. Not perfect, but it's as good as we can do with the information that we have. Is this function increasing or decreasing? Well, it's fairly clear as we go from left to right that this is an increasing function. Moving on to question 13. To the nearest tenth of a foot, what is the predicted average height of the tree at 20 years of age? So here what we would want to do is make sure that we set up our windows so that our x max is bigger than 20, so the x is the age, and then we can just do trace, type 20, and then enter. Or we could come back to the equation that we had up in question 11 here, and we could substitute a value of 20, there we go, in place of this time. It's a 20, not a 26. There we go. If we plug that 20 in and evaluated this, then the result that we would get is that at 20 years of age, the expected height of the tree will be about 24.8 feet. So I'd encourage you, if you haven't done the calculation yourself, either plugging into the equation or by using the trace feature on your calculator, pause the video at this point and make sure that you do get that answer. Then as we finish off looking at question 14, to the nearest tenth of a year, what is the average age of a tree that is 11 feet tall? So now what we want to do, and I don't think I have a graph here, and so I'm just going to do a rough sketch of what we'd be looking at. Well, maybe I can do it on the grid above here. So as I look at this, I would want to draw a line. And I don't know what my scale is here, but let's just pretend this line is, we'll undo. I want to make that straight across. There we go. What we're looking for is, if this is y equals 11, we want to find out what is the x-coordinate of this intersection point. So we would graph y equals 11, we'd graph our regression equation, and then we'd find this intersection point here, and then use that to figure out what is the x value that we get that would correspond to that intersection. So I'd encourage you to pause the video and do that calculation on your graph, restart the video, and then compare your answer to mine. Well, here's my answer. The average age of the tree that's 11 feet tall will be about 2.2 years. So what I drew up here is way off. So not knowing what the scale on the y-axis was, I just did kind of a rough sketch. There we go, 2.2 years. And that's how we do logarithmic regressions and application questions that make use of data. So here's some practice questions for this lesson, not super long. Again, make sure you do practice on solving logarithmic equations. That's really the key challenge in this chapter. All right, that will end this lesson.